In this video, we're picking up with our pre-lab assignment. We were discussing the solubility table and trying to selectively precipitate sodium carbonate or sodium chloride. And we had decided based on the solubility table that the carbonate would be much easier to precipitate out over the chloride. And therefore, when we checked our solubility table, we saw that a first name such as barium, barium carbonate is insoluble as a product, whereas barium chloride remains soluble as a product, and therefore all we need to do is introduce some barium ion in our solution and it will indeed precipitate out the carbonate if it's there. And so we need a last name on the carbonate, and again, just because it's written first, it's very convenient knowing that acetates are always soluble. I'm going to just introduce barium acetate as the reagent that will selectively precipitate out in our station 1. And so let's do the chemistry, and this is what we actually have to write. So we're going to introduce some barium ion into that solution, and so we said that we would use barium acetate. Ba is the ion that we'll introduce. Ba is a +2. And knowing that it will precipitate out the carbonate, CO3 2 negative is carbonate. And again, just turning this into a net ionic equation, BaCO3 will form, and I'll just use a down arrow to let you know that that is the symbol used to represent precipitation. So introducing the barium ion, and the label literally would have to say barium acetate. It needs a last name. And so the label that you would find at your reagent station, BaC2H3O2, and that would introduce the barium ion to selectively precipitate carbonate. Of course, barium acetate with sodium chloride, no reaction. And so based on observation, if the chloride is present, we would not see a precipitate, and if the carbonate is present, we would see a precipitate. So the power of observation would let us decide which of the two salts was indeed present in the jar. How about station B? If we were testing nickel chloride or barium chloride. Notice again we have some interesting things right off the bat. They have the same last name in this particular case, so that would not be used as a separation tool, but they have different first names. We notice that nickel chloride and barium chloride are both water soluble, and so again, based on the solubility table or the rules there, we would see chlorides are always soluble unless their first name is silver, mercury, or lead. And on this table you can see that they are both soluble. Just checking out the solubility table here. Here's the chlorides. Alrighty, and then of course nickel, and you can see nickel on this chart. But the most helpful one would be right here. Then they're both water soluble. All chlorides are soluble unless they're silver, mercury, or lead. And so with this example, both are water soluble. So what next? Is one of the positive ions a transition metal and the other a representative metal? And here the answer is yes, indeed. With this particular solubility table you have in front of you, we talked in the previous video about colored solutions. Nickel happens to be a transition metal that when dissolved in water gives the appearance of a nice green color. So I can exploit the different physical properties to tell the difference between nickel and barium chloride. Since the nickel is a colored transition metal, all I'm going to do is dissolve those salts in water and see what color it comes out to be. So if nickel chloride is present as a solid salt, I'll just write that as NiCl2, nickel 2 chloride. And I'm just going to place above the arrow the water, just to let us know it's not truly a chemical reaction, it's just a dissociation, that the nickel ion, when released with its 2 positive charge, would be an aqueous ion, and we'd have 2 chlorides come out, aqueous ions, and that this right here is a green color when dissolved in water. If I dissolve the salt in water and it turns green, I would know nickel chloride was my salt. However, if I dissolved barium chloride in water and it remained colorless, it would not be nickel. So I could just tell one from the other based on the color it turns when it dissolves. Station C has us investigate potassium chloride or ammonium chloride. Again, we have the same last names, so that would not be helpful in determining the identity, but we can hone in on the first names. Both are water-soluble salts. Neither positive is a transition metal, and so I'm not really testing for colored solutions as in the previous station. And I noticed that both positive ions are always soluble in water. Alkali metals and ammonium are part of the always crowd. But what I can do is notice that ammonium has a root word based in a strong ammonia smell. And this comes back actually from our spot testing in the last experiment. Spot testing said if we took ammonium, and so I'll just write that as ammonium with its positive ion, and I'm just releasing that spectator chloride. And I add a strong base, let's say sodium hydroxide sitting at the station. This would be called your reagent. And again, the sodium will be a spectator. Ammonium chloride, I'll just go ahead and write this so you can see the double replacement. Ammonium chloride with sodium hydroxide. We form ammonium hydroxide. And again, the two spectator ions would be the sodium chloride. And here, as soon as this guy forms, we understand that it is unstable and immediately decomposes and releases the ammonia gas and water. My pen isn't working well this morning. So we have ammonia and water. So again, what I would want us to do in terms of writing out spectators, let's get rid of the sodium ion, let's get rid of the chloride ion. NH4 plus OH negative makes NH3 plus H2O. Eliminate the spectators, it has us write the net ionic equations only. And again, this is gone because it decomposed, and this was the driving force. The odor of ammonia, the gas, would be used to distinguish between ammonium chloride and potassium chloride. So I would add that strong base and very carefully waft the odor, and if I smell ammonia, I've identified ammonium chloride, and if I don't smell ammonia, it must have been potassium chloride. So here we're using a physical property of odor. In the next station, we derive sodium hydroxide, or I think I skipped a station there. Letter D. Sodium hydroxide or magnesium hydroxide. Alrighty, same last names, different first names. And this is a reminder to always check the solubility table first for water. One of the easiest tests right off the bat is to distinguish them based on their solubility in water. And hydroxides is this column here. Notice that magnesium hydroxide is not soluble in water. Alrighty. But the little A here says it is soluble in acid. So it does not have great solubility in water. Whereas sodium hydroxide, and that's down here, sodium hydroxide is water soluble. Again, that alkali metal as a first name, always soluble. So this test is just as easy as dissolving in water, and you'll be able to decide if it will dissolve or not. Sorry, that's my dog. So we'll say sodium hydroxide as a solid when placed into water would create aqueous ions of sodium and hydroxide. And so if I take my unknown salt, dissolve it in water, and it does break apart and form a colorless clear solution, and otherwise it dissolves very well, I've identified it to be sodium hydroxide. But if I take magnesium hydroxide and place it into water, and I stir, 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 and nothing happens, no matter what kind of agitation or convincing, it doesn't dissolve well. And I can just quickly eliminate one from the other based on the solubility test. One will dissolve well in water and the other will not. How about potassium acetate or potassium thiocyanate? This is letter E. And here I'm reminded of a spot test plate from a previous lab. This is a lab from a couple weeks ago. We have the same first name, so that's off the plate. They're both water soluble, so I can't just simply dissolve and make an observation as in the last lab. So I have to think about selective precipitation. And I remember working with this potassium thiocyanate last lab, and we introduced the iron nitrate and noted the deep red color. Acetates are always soluble, but I can get the potassium, the thiocyanate, to precipitate out by introducing the iron ion. So as a reagent, I would add iron 3 nitrate so that I can selectively precipitate out the thiocyanate and look for that deep red color. So again, relying on things from the previous lab, noting this color, SCN carries a -1, iron is a +3, so we'd have to balance with 3 there. And keep that balanced, and notice that this is that red, deep red color that we would be looking for. Alrighty. Potassium acetate, upon the addition of iron nitrate, no reaction, just remains, well, it would have that yellow tinge of what the iron started as. But this definitely would have a color change if indeed the thiocyanate was present. Station F, sodium hydrogen sulfate, or just plain old sodium sulfate. Same first name, so the sodiums are not unique. Take them off the table as a way to identify them. But here we have a bisulfate, or sometimes just referred to as hydrogen sulfate, versus sulfate. So we have HSO4 versus just plain old SO4, hydrogen sulfate. Now, do you remember a lab very similar to this? We were trying to determine if we had potassium or sodium bicarbonate or sodium potassium carbonate. That hydrogen actually decomposes upon heating, and therefore we can detect the identity based on a mass lost. So if indeed my, let's just write sodium hydrogen sulfate because it starts solid, and I place it over a flame, and so I'm just going to denote that by saying a little arrow there, out comes a little bit of mass loss. So we end up going straight to the sulfate, and we release actually sulfur trioxide and water vapor. This comes out as a gas, and this comes out as a vapor gas, and therefore, oh, I should balance this quick. Alrighty, there it is. If I indeed started with hydrogen sulfate and upon heating it, I end up with sodium sulfate. We've lost sulfur trioxide gas from the dish. We've lost water vapor from the dish. The test is to see if it loses weight. So I could clearly start with my unknown compound, weigh it, heat it, weigh it again, and if it lost a significant amount of weight, I've identified it to be hydrogen sulfate. If it did not lose any weight, we knew it started as sodium sulfate in the beginning. So there would have been no chemical change had I started with sodium sulfate and ended with sodium sulfate upon heating. Alrighty, so the weight loss test, as done in a previous experiment, would help us in Station F. Making good progress. We go to the next station, Station G, magnesium carbonate or barium sulfate. Alrighty. So there's no common ion here. They have no common first name, no common last name. Check your solubility table and you'll notice that both are insoluble in water. So that's not a good way to test. We test then for the third thing, so we test for selective precipitation, water solubility, acid solubility, and now we're noticing nothing's working so far. So if I check the acid solubility, magnesium carbonate is not acid soluble, but barium sulfate is. So let's pull up that chart, just make sure we know what I'm saying. It's this particular solubility table that has the A's and the P's and the S's in it. Alrighty. Find on your solubility table magnesium carbonate. So here's the carbonate, and here is magnesium. Magnesium carbonate has a P in it, saying it's insoluble in water as a product. Alrighty. How about barium sulfate? So sulfate is way over here, and barium right here. Barium sulfate. Notice here's a little A. We can exploit the difference here. We have magnesium carbonate insoluble. Even in acid it won't be soluble. But I can get barium sulfate to dissolve into an acid. Little a stands for slightly soluble in acids. So at this particular station we're going to need to dissolve an acid and decide what we see. So again, checking this out, what we've noticed is that I can exploit the acid solubility. Alrighty. Magnesium carbonate would not dissolve an acid, but barium sulfate would. So again, what I would like to do is just to show the solid barium sulfate. And over the arrow as a solubility test, I'm going to put a strong acid, and a nice common acid would be something like hydrochloric acid. Alrighty. In acid, I can get it to dissolve. We'd have the aqueous ion of barium, and we'd get the aqueous ion of sulfate. Alrighty. So a colorless solution that dissolves completely. Stir it up, agitate it, and you can get it to dissolve. But if I did this test and that compound did not dissolve, I know that it would be magnesium carbonate. It does not even dissolve in a strong acid. So MgCO3 behaving in acid, and again I like to set that over the arrow so you know it's not a chemical change, it's just a physical dissolving process. We'd have no reaction, and therefore I can use that to distinguish the identity between those two solids. Letter H would have us investigate zinc carbonate or cadmium carbonate. Alright, so same last names, different first names, zinc versus cadmium. Although they're transition metals, neither are colored in solution. So again, once I notice that the first names are transition metals, I tend to check this out. Zinc and cadmium don't happen to be colored. Here's zinc, here's cadmium, no distinct color in solution, so that's off the table as a way to distinguish them. And both are insoluble in water. Neither dissolve well in acids, but finally, based upon that checklist, I check water solubility, then I check acid solubility, then finally base solubility. Alrighty. So this is the tool page, finally, that I would default to for checking out zinc versus cadmium carbonate. It's this tool way to the right. Notice that zinc, OH negative and NH3 is what's listed here. And versus the magnesium, cadmium. See the distinction? I can exploit this right here. What makes zinc different than cadmium is being dissolved in a strong base, such as hydroxide. They both behave the same with ammonia. They would form a complex ion, but where I can tell them apart, cadmium will not form a precipitate with hydroxide, but zinc will form a precipitate with hydroxide. So there finally is the distinguishing characteristic between these two. We're going to use the hydroxide. I'm going to get to the right slide. Here we go. So I'm going to add OH negative. Zinc will form a complex ion, but cadmium would not. So I would simply show the net ionic equation with zinc ion being introduced with some sodium hydroxide, but I will just eliminate the spectator sodium. And I'm going to keep the charges balanced by introducing 2 units of OH negative, and we would form zinc hydroxide and this would be your solid precipitate. Cadmium introduced to hydroxide would remain soluble. Zinc introduced to hydroxide would precipitate. So adding a strong base allows us to distinguish between the two. Letter F. Is it silver chloride or silver oxide? Same first names but different last names. So silver chloride or silver oxide. Both are insoluble in water, so I can't get them to dissolve. But I go to the acid solubility table and I find a distinguishing characteristic. So the test here through default is by testing for acid. Now let's be clear, just kind of go back up and look at your chart so you understand where I'm coming up with these tests. Silver chloride versus silver oxide. So silver, I'm going to scroll way down, pull it up on the screen. Here's silver. All right, silver chloride has a little A in the box. Alrighty. Silver oxide has a P in the box. Now that can be used to tell them apart. P means it's insoluble in water, insoluble in acid. But the little A here says insoluble in water, but it will dissolve in acid. So that's my test to distinguish between a chloride and an oxide of silver, noticing that one has a little A and the other has a P. The acid test will be used to distinguish the two. So I'm going to take a little bit of the sample from the unknown jar and dissolve it into a strong acid and observe, does it dissolve well? And so we said, whoops, I leaned my hand on the wrong spot. So we have silver chloride in acid will dissolve. So the chemistry simply looks like AgCl. And then over the arrow, I'm going to just place the strong acid, and again, I'll just select HCl, although there's a variety of strong acids. That's the most common in the lab. And then we'll form aqueous ions of silver and an aqueous ion of chloride. And again, it would be a colorless, or actually silver tends to have a little gray tinge to it, but in our sense, it will be colorless. And if it had indeed been silver oxide and I put it into acid, I could not get it to dissolve. So what I'm looking for is a solubility test. Can I get the sample to dissolve well in acid and use that to distinguish between the two solids? And finally, our last station would have us investigate zinc sulfide versus copper sulfide, letter J. Same last name, sulfides, but different first names. And again, both are insoluble in water. Check your solubility table and verify what I'm saying. Neither will dissolve well in water. Both dissolve in acids, but copper is a transition element, and it will dissolve in an acid and turn blue, and zinc will not do that. So again, I go through my checklist. They're both insoluble in water, so I check acid. Both dissolve in acid, so then I check base. I go through that progression and try to find a distinguishing characteristic. And what I'm noticing from this chart, here it is, copper actually, when dissolved, turns blue. Alrighty, but zinc, when dissolved, does not have a color. So even though I can get them both to dissolve into acid, I can check the color once they're finally dissolved in there. And I can just pull out some acid, dissolve them in there, and see if it turned color. And that's what we'll do. We'll take a little bit of the copper ion, and I'll just say that we're using CuS, and we'll place it into an acid, such as HCl, and we'll form the aqueous ions of copper, and that would be a +2, and the aqueous ion of sulfide, which carries a -2, and this does dissolve, and it will turn blue, a copper-colored blue. If I did this to zinc sulfide, it will indeed dissolve, but it will not turn a color. So we've practiced many different styles of selective precipitation, water solubility, acid solubility, base solubility, colors. All of these unique, and there was a weight loss for one of them, all of the properties that can be used to distinguish between two compounds. So what's great about this lab is it's making you pull from a wealth of resource, from experience from all the labs prior. Again, your lab will have 26 stations set up. The reagents will be provided for you. You just have to figure out how to test for them and identify the unknowns. See you at lab this week.